This is the screencast for section 10.1, example 4. We're going to look at some cycloids. Suppose that a wheel of radius A rolls along a horizontal line without slipping. So this wheel here is rolling along the horizontal axis, the x-axis. The path traced by point P. So this point P, if we trace it all the way through this curve as the wheel is spinning, that curve is called a cycloid, where P is originally at the origin. So P started here. Now we want to find parametric equations for the path of point P. All right, well, the path of point P, if it's parametric, is going to be a function of x and a function of y of t. So let's look at x first. X is the horizontal distance so far. Now the horizontal distance so far is up to the center of the wheel, and that, if we look at, is going to be the circumference or portion of the circumference that has rolled along the ground, we'll say. So in other words, we're looking for arc length. So we can say arc length is the total distance traveled. Well, arc length we know is S equals R times theta, theta being in radians. And then R, the radius, we're calling A. Theta, we're calling T in this. You can see T is the angle moved so far in this diagram. So in that case, the horizontal distance so far is just going to be A times T. Now, it's not only just the horizontal distance it's moved so far, it's also a relationship then of the distance that P is from the center, the horizontal distance. So the horizontal position within the circle can be represented by just A times the cosine of theta from this triangle. And cosine might be negative and cosine might be positive. Now y is the radius off of the x-axis. So it's going to be a total of A, but then this wheel is, or the point P is moving, so sometimes it's going to be more than A. As you can see here, it's going to be a distance of A plus a little bit. Sometimes it's going to be less than A. So that vertical position in the circle can be represented by A times the sine of theta. Again, sine will be positive when the point is above the center of the circle, and negative when the point is below the center of the circle. Well, now the problem is that we've got t and theta in our parametrizations. So we can't do that. So let's find a way to express theta in terms of t, because theta is just the little angle inside this reference triangle we're using. T is the full rotation so far. All right, well, theta is going to be the angle from the start to the positive x-axis. Now the angle is starting down here, so this would be the initial position of P down here. Now the positive x-axis standard form is over here, the horizontal axis on the right. So we already are starting out with 3 pi over 2 radians. So the angle from start to the positive x-axis is a beginning of 3 pi over 2 radians. Now we're going to take away the partial angle traveled because that's in the opposite direction. So we're not going 3 pi over 2 counterclockwise, we're going t clockwise. So we're going to take away the partial angle. Now remember, this wheel is continuing to spin and spin and spin and spin and spin. So then we also can add a number of full circles that have been completed, so 2k pi is fine. And k will just be the number of complete circles. So we're looking at coterminal angles with this. Well, now that we know what theta is, I can start to put together what P of x comma y is. X is A times t plus A cosine of theta. Y is A plus A sine of theta. And we just said that theta is going to be 3 pi over 2 minus t plus 2k pi. Well, that's a bizarre expression right there, so let's try and simplify and think what that means. 2k pi are full circles. Okay, so those, I don't really have to worry about those. Those are coterminal angles. Really all I'm worried about is 3 pi over 2 minus t. Now that 3 pi over 2 minus t, that's a vertical flip over the x-axis of cosine and then a shift right 3 pi over 2. So, that's going to get me the opposite of the sine of t. So that means x can be written as at and now minus a sine of t. And then y, pretty much the same concept. We have coterminal angles, and we're looking at the vertical flip of sine over the x-axis, and then a shift right 3 pi over 2, which is going to be the opposite of cosine of t. So that means y can be written as a minus a cosine of t. And that would be my parametrization of this cycloid, the path that P, a point on the outside of a wheel, is taking as it spins along its path. The now try problem number 41 asks us to look at a Curtate cycloid. So we're going to modify example 4, what we just did, slightly to find the parametric equations for the motion of a point in the interior of a wheel of radius A as the wheel rolls along the horizontal line without slipping. So now our point isn't all the way on the outside on the circumference of the wheel, it's going to be somewhere on the inside of the radius, so shorter than the radius. And we're going to assume that the point is at distance B from the center of the wheel. So this distance is B, which is going to be shorter than A. And then this curve, known as the Curtate cycloid, has been used by artisans in designing the arches of violins. So I went and looked this up at wolfram.com. Wolfram is where I get a lot of my visuals for you guys, as well as they invented this program called Mathematica. I was able to take a couple classes in college using Mathematica. It is basically a different kind of language that solves complex math problems. Pretty cool. But anyway, here is what a Curtate cycloid looks like. See how the point is on the inside of the circle, not along the circumference. And then if we follow that path of the point throughout its rotation, this graph would then be a Curtate cycloid. So we need to find an equation for this. Well, it's very similar to example 4. The main change we made is that the amplitude of the curve, or the height of the point, or the, quote, radius that we're using, was A and now is B. So that just means that x is going to be A times t, the distance total traveled, minus B, the new amplitude, times the sine of t. And then y is going to be just A, still the height of the center of the wheel is the radius, but then we're going to subtract now a new amplitude B, cosine of t. And of course that would have to be for a B, a new distance from the center of the wheel that is smaller than the radius.